So in last lecture, so we are revised the syllabus of MAT-401, that is numerical methods. So what is the actual syllabus of this course? So we have seen, and also we have seen the weightage of this course. So distribution of weightage according to chapters. So which chapter is most important and which chapter is as compared to remaining chapters. So whether it is important or not. So in that we have seen the chapter interpolation is most important chapter of this course. So total there are 5 chapters. So first chapter, that is solution of algebraic and transcendental equations. Second chapter, that is interpolation. Third chapter, that is curve fitting and approximations. And sorry, fourth chapter, that is solution of linear system of equations. And last chapter, that is numerical solution of ordinary differential equations. And I have give already some stars for the chapters according to their weightage. Weightage means weightage in your final examination. See, so first chapter, so I have given 2 stars. For second chapter, I have given 4 star. For third chapter, I have given 2 star, or I can less 1 star for the chapter. So I can give 1 star or 2 star. So this chapter is not important, but because yeah, if we delete this Chebyshev polynomial from the chapter, then I will give 1 star, that is single star. And if I add Chebyshev polynomial and economization of power series in chapter number 3, so I will give 2 stars for the chapter. And fourth chapter, it is also important chapter, that is solution of linear system of equations. In that we will see so many methods to solve system of linear equations, the direct methods and indirect methods. So already we have seen it here in short. So in the chapter, so we will see 3 direct methods, that is Gauss elimination method, Jordan method, and method of factorization. It is also called yearly factorization method. So in indirect methods, you will see Gauss serial iterative method and Jacobi's method. So that is chapter number 4. And chapter number 5, that is numerical solution of ordinary differential equations. So in that you will see total 4 methods, not 4, but there will be 5, because there is modified Euler's method is also there. So third method, in third method there are 2 sub methods, you can call it as. And in fourth method also there is Runge-Gupta fourth order and second order method. So totally, so there are 6 methods to solve ordinary differential equations numerically. So numerical solutions of ordinary differential equation, that was the last chapter. So already we have started first chapter. So what is first chapter? That is solution of algebraic and transcendental equations. So in that, so already we have seen, sorry, so in that, so we'll see 3 methods to solve algebraic and transcendental equations. Means these 3 methods are useful to solve algebraic as well as transcendental equations simultaneously. So in that, already we have started first method, that is bisection method. See, yeah. So solution of algebraic and transcendental equations. So in the chapter we will see 3 methods, that is bisection method, falsification method, and Newton-Raphson method. All this part already we have seen in last lecture. So first chapter. So for that, just we have seen some introduction. So what is algebraic equation and what is transcendental equation? So last time we have seen it. What is algebraic equation? Yeah. What is algebraic equation? An equation which contains only polynomials, purely just contains polynomials, is called algebraic equation. Means fx equal to fx is polynomial. If you consider this equation, that is fx equal to 0, this is one equation in x, variable x. So there is only one variable, that is x. F is a function of x, and that is equal to 0. So if fx is purely polynomial, then resulting equation is called algebraic equation. And if fx contains For example, combination of exponential function, polynomial function, trigonometric function, logarithmic function. Then resulting function will be, resulting equation will be transcendental equation. An equation which is not an algebraic equation is called transcendental equation. It means it will contain exponential term as well as trigonometric terms or logarithmic terms. So an equation is algebraic or transcendental, it depends on this fx. So already we have seen it. So in introduction, what is algebraic equation and what is transcendental equation? So that part is clear, and we have already discussed in last lecture. So yeah, 6 participants. So next we'll continue. So this chapter and we'll just introduce bisection method. So yeah, yes. So before that, last time, so we are in position to define, see, solution of algebraic or transcendental equation. What is the what is the definition of solution, or it is called root of that equation? So fx equal to 0. So it may be algebraic equation or transcendental equation, that depends on this. If x equal to 0, for some you can take, for some c belongs to, so you can take set of real numbers or you can take set of complex numbers. So I'm deleting this part here. For some c, just double write, then c is called solution of fx equal to 0. It may also call root of that equation. See, it is also called root of fx equal to 0 or root of this polynomial. Already you have used this word, that is root of polynomial. So what is solution of? What is title of the chapter? That is solution of algebraic or transcendental equation. So what is solution of algebraic or transcendental equation? So if fc equal to 0 for some c, then c is called solution of fx equal to 0. So in the chapter, we'll find this c using some numerical techniques. And for that, so there are three particular methods. So first method, that is bisection method, second method, that is falsification method, and third method, that is Newton-Raphson method. Also there is modified Newton-Raphson method, but we will see it afterwards. So just start. First method, that is bisection method. So before that, there is one well-known theorem, and we'll just revise this theorem. And this theorem gives us the location of root of given algebraic or transcendental equation. See, so statement of this theorem is that it is very important, and statement of this theorem is here. See, if the function fx is continuous in the closed interval ab, and if fa and fb are of opposite signs, then there exists at least one real root of fx equal to 0 between a and b. So see, what is statement of this theorem? Yeah. See, so this theorem is also called intermediate value theorem. So if the function fx is continuous in the closed interval ab, and if f and fb are of opposite signs, then there exists at least one real root, sorry, it should be real root of fx equal to 0 between a and b. So this is statement of this theorem. It means that, see, suppose it is x-axis and it is y-axis. So there is one function that is fx, and we have algebraic equation. Suppose it is fx equal to 0. If we draw y equal to fx, then its graph will be, so between a and b. You can draw its graph. Just a minute. See, see, f of a is positive, f of b is negative. So suppose it is a and it is b. So at a, the value of this function is positive, means f of a is here somewhere. So this point will be, see, it will be 0 f of a, and its value at b is negative, means f of a and f of b have opposite signs. So f of b will be here somewhere, means graph of this function will be like this. If f of a is positive and f of b is negative, means f of a and f of b have opposite signs, surely between a and b, the graph of this function should intersect x-axis at least once. It may intersect more than one, but at least once it should intersect x-axis. So what are the coordinates of this point? See, it will be 0 f of b. So if its graph is like this, then surely at some point, suppose this point is c, at point c, at least this function intersects x-axis. So this is the statement of this theorem. Surely this function should be continuous function in the closed interval AB, and if FA and FB have opposite signs, then there exists at least one real root for fx equal to 0, means at least one c belongs to R. There exists at least one c belongs to R such that f of c will be 0 between A and B. And its geometrical interpretation you can see here. So geometrical interpretation of theorem star you can write, of theorem star. So what is geometrical interpretation? Actually, so this theorem is called method of tabulation here. If the graph of continuous function lies above the x-axis at one endpoint of interval AB and below the x-axis another endpoint, then it must cross the x-axis somewhere in between at least once. In between means in between A and B. It should intersect x-axis at least once. It may intersect more than one point, but surely it will intersect at least one point. So this is statement of this theorem, and we'll use this theorem in method of bisection or bisection method. This is the, see, basic principle of this method. So what is bisection method? Let us see. So this method is also based on Bolzano's theorem on continuity. So this theorem is also called Bolzano's theorem of continuity. Bolzano's theorem of continuity. So this statement of this theorem, and we'll use this theorem in bisection method. See, what is this method? So let fx equal to 0 has a root in closed interval AB. Surely, so this function has real root in the closed interval AB. The function fx being continuous in closed interval AB, because that function is continuous in closed interval AB. So using this Bolzano theorem of continuity, surely this function graph of this function intersects x-axis at least once. So then f of a and f of b are of opposite signs. So it is there, surely. So f of a and f of b have opposite signs, therefore product of fa and fb should be negative. So if fa is positive and fb is negative, so the product will be negative. Or fa is positive, fb is negative, surely the product will be negative. So both fa and fb have opposite signs, so surely the product is negative. So what is next? So I will write it in short or algorithm. What is bisection method? Step 1. What is bisection method? See, let's suppose fx equal to 0 be given algebraic or transcendental equation. It may be algebraic or it may be transcendental. See, so what is step 1? Step 1. Find, see, you have to find such a and b such that fa and fb have opposite signs, means fa into fb is strictly less than 0. Means fa and fb both have opposite signs. So that is our step 1. So then f and fb are opposite signs. If there exists at least one real root between a and b, surely f and fb have opposite signs. So it is there. So first you have to find such points a and b. If it is not given, if you have given interval, then simply you can find its mean. So what is next? So so in first step already you find a and b. And what is condition of a and b? So at a and b, function have opposite signs, means fa into fb is negative. So what is the next step? So let x1, which is mean of a and b, means a plus b divided by 2. See, so next, so this is suppose a and this is suppose b. So what is next? Find x1. What is x1? x1, which is mean of a and b, that is a plus b divided by 2. It will be, surely it will be at middle of this interval AB, which is midpoint of A and B. So it will be here. So x1, which is a plus b divided by 2. So next you will find value of f of x1. What is x1? So this is middle point of A and B. So next, simply find out f of x1. Then find f of x1. So if you find value of f of x1, if f of x1 is 0, then what happens? If f of x1 is 0, then x1 will be our required root. Then x1 will be required root of or required solution of given algebraic or transcendental equation will be required root. If f of x1 is not equal to 0, then what happens? See, if f of x1 is not equal to 0, then it may be positive or negative. Then f of x1 will be strictly greater than 0 or f of x1 strictly less than 0. It may be positive or negative. Surely it will be. If it is not equal to 0, because there are only three possibilities for f of x1, it may be 0 or positive or negative. See, surely. So what is next? Then x1 is the root of fx equal to 0. Otherwise, either fa into f of x1 strictly less than 0 or f of x1 into f of b still less than 0. At least one. See, then, so what we'll get? Then f of a into f of x1 means f of x1 is either positive or negative. And surely f of a and f of b have opposite signs. Suppose we can consider, so here f of a and f of b. So f of a is positive, suppose, and f of b is negative. Their sign is positive and negative. And if fx1 is also positive, so already fa is positive, f of x1 is positive, then what happens? So fa is positive, f of x1 is positive, so root will not lie between a and x1. So next time we'll omit this interval and we'll consider our interval x1 and b. So next we'll write still less than 0 or f of b into f of x1 still less than 0. Surely it will be there. See, implying that the root lies in the interval x1 into b. See, thus the interval is reduced from ab to either ax1 or a1b. See, suppose, see, f of b into f of x1 is negative. Then, see, surely, so in that case, f of a into f of x1 is not 0. Either this is negative or this is negative. See, so surely, what it imply? See, so what is our situation? Our situation is like this. See, so this is a, this is x1, and this is b. So f of a, at f of a, so function has positive value. At f of x1, it also have positive value, and at b, the function has negative value. So value of f is positive, value of f of x1 is positive, and value of f of b is positive. So what is our Bolzano continuity theorem? Our Bolzano continuity theorem tells us that if, see, a and b have opposite signs, then surely there exists root. If both have same roots, same values, then root does not lie in between these two. So surely root does not lie between this interval. So next time we cut this interval. And what is our resulting interval in next step? So it will be, say, so hence root lies between in the interval x1 and b. So what is step 2? Again you'll find mean of these two. So what is our resulting interval here? Our interval is x1 and b. See, so at x1, f of x1 is positive and f of b is negative. So in step 2, find x2. What is x2? It is x1 plus b divided by 2. That is mean of these two. So next, also find f of x2. So x2 is here. So find f of x2. If f of x2 is equal to 0, then x2 is the required root of required root of given equation, or you write fx equal to 0. See, if f of x2 is not equal to 0, then so in similar way it may be positive or negative. Then f of x2 is greater than 0, or f of x2 is less than 0. So you'll continue this process. If fx2 is positive, then what happens? See, if fx2 will be positive, so again you will cut this interval because f of x1 is already positive, f of x2 is again positive. So our root does not lie between these two because both have same sign. So what is that theorem tells us? That theorem tells us that if both fa and fb have opposite signs, then root lies between a and b. So here, if f of x2 is positive, then root lies between this interval. So again we cut this interval, and if it is not positive, it is negative, then what happens? So it is already negative. So f of x2 is negative, f of b is negative. So our root does not lie between this interval, and we will cut this interval. See, so our resulting interval in next step will be x1 and x2. So we'll continue this process. So let us see here. What is step 2? So this step 1 and this step 2. What is step 2? The here x2 is a1 b1. So notations are different. The middle point of a1 b1. If f of x2 is 0, then x2 is the required root of fx equal to 0. Otherwise, you will continue this process. So we'll continue this process repeated until root is obtained to the desired accuracy. So what is the meaning of desired accuracy? Let us see. So we'll find it after some solving some problems. So suppose you get value of x5 is equal to 2.37093. If you get x6 equal to 2.37009, suppose 2, then x7 will get suppose 2.37009, suppose 1 2, likewise. So up to 4 decimal places you can see, that is 3709, 3709. So this pattern is going to repeat. So if you ask, find the root of given polynomial up to 3 decimal places or 4 decimal places. If they ask you to 4 decimal places, and if two continue values of x are equal in first 4 decimal places, then you can stop this process. Otherwise, you will continue this. So in such situation, you will stop this method. So you have to continue this method up to 4, 5, or 6 iterations. That depends on so which accuracy you have asked to find. So afterwards, in problem, we'll see all these things. So next, we'll solve some problems. Just a minute. So it is very important. You have to use scientific calculator. Okay. So we'll solve one problem. Yeah, yes, we'll solve this problem. So example, find a real root of, suppose polynomial is fx equal to, we can take x cube minus x minus 1 equal to 0 by bisection method, and correct up to 4 decimal places. So solution. So let here, what is fx? Fx equal to x cube minus x minus 1, and that is equal to 0. So it is given. So what is first? So let's suppose a. What should be value of a and what should be value of b? So here you can take it by calculating fx at some points, some integers. So note that it's very important. You should purchase scientific calculator. It is very important because you have to use calculator to calculate these calculations, and in some problems you have to use so advanced operations. So for that, so you require fx991 calculator or more than that. So let us find a and b at which fx have opposite signs. Means tell me value of a at which, suppose if fx is positive, and value of b at which f of b is negative. So let's take suppose a equal to 1. So what is value of f of 1? It will be 1 cube minus 1 minus 1. So what is that? It is equal to minus 1. So which is less than 0. See, and so let's take suppose b is equal to 2. So you have to find these values a and b by practice. So what is f of 2? It will be 2 cube minus 2 minus 1, that will be 8 minus 2 minus 1, that is 5, and we just click a line 0. So hence you can write, see, f of 1 into f of 2 is less than 0. So therefore, using Bolzano continuity theorem, there exists at least one root to fx equal to 0 in the interval that is 1, 2. Surely there exists at least one real root for this function fx equal to 0 in the interval 1, 2. So what is our next step? See, so step 1 you can call it as, or you can call it as iteration 1. See, so you'll write it as step 1. So what is x1? x1, that is 1 plus 2 divided by 2, and it will be 1.5. Is it okay? So you'll call it as x1, or you can call it as 0. That depends on you. See, so what is f of x0? That is f of 1.5. But what is fx? So fx is x cube minus x minus 1. So this is fx. So let us find f of x0. That is 1.5 its power 3 minus 1.5 minus 1. And what is the value of this? So 1.5 its cube. So what is that? See, yeah. So you can find value of 1.5 cube, or I'll write it as, that is 3.2 its power. So this value is nothing but 3.2. So its power 3 minus 3.2 minus 1. So it will be, see, 27 upon 8. Is it okay? Minus 3.2 minus 1. So it will be 27 upon 8 minus 12 upon 8 minus 8 upon 8. So that will be 7 upon 8, which is strictly greater than 0. So here f of x0, that is f of 1.5, is positive. That is, you can write f of 1.5 is strictly greater than 0. So already, what is situation? So here, situation is that, see, what is our interval? So this is A, this is B, value of A that is equal to 1, and value of B that is equal to 2. So f of 1 is negative, f of 2 is positive. It is there, and you find middle point, that is midpoint of 1 and 2, that is 1.5. So you call it as 1.5. What is f of 1.5? So it is equal to positive. See, so f of 1 is negative, f of 1.5 is positive, and f of 2 is also positive. So if same sign, so you'll cut this interval. So this interval is not there. See, so this interval will cut in next process. So we'll cut this interval, and what is our resulting interval? So our resulting interval, our root will lie between 1 and 1.5. So in next step, we'll continue this. See, so next we'll write hence, yeah, yeah. Hence our root lies between between 1 and 1.5. So what is our next step? Step 2, or you can call it as iteration 2. Find x1. What is x1? That is 1 plus 1.5 divided by 2, and it is nothing but 1.25. It's okay. So next, so therefore, what is f of x1? That is x cube minus x minus 1, which is nothing but, sorry, x1 cube minus x1 minus 1. So which is nothing but 1.25 cube minus 1.25 minus 1. And it is nothing but, so what is cube of 1.25? So it is 1.95 minus, so it will be 2.25, and that is equal to minus zero point 0.3, which is less than 0, that is negative. So f of x1 is negative here, you get. See, so what is our situation in this iteration? So it is like this. So this point is x1, sorry. So this is a, and this is x1. So a is 1, x1 is 1.5, sorry, this is x0, and this is x1. X1 is 1.25. So this situation of this iteration. So what is f of 1? F of 1 is negative, and f of 1.5, which is already positive. And what is f of 1.25? It is negative. So f of 1 is negative, f of 1.5 is negative. So in next step, so this interval will be deleted. So we will not consider this interval because both have opposite signs. We require opposite signs. Then root lies between these two points. So what is our resulting interval in next step? So using Bolzano continuity theorem, hence root lies between 1.25 and 1.5. So you can continue this process. Continue at home. So in next lecture, we'll solve some more examples. Till then, we'll stop. If you have any query, so you can directly message me or you can call me.